Before 2017, sequence models like recurrent neural networks, or RNNs, were the standard for natural language processing. These models read text the way a human does, processing data through temporal, step-by-step unrolling, moving from left to right, one word at a time. This creates a strict mathematical bottleneck. In an RNN, each hidden state is a function of the previous hidden state and the current input. Because position t cannot be calculated until position t-1 is complete, the model executes O of n sequential operations. This sequential structure prevents the model from being parallelized within training examples. Modern GPU architectures are built to execute massive calculations simultaneously. However, because an RNN must wait for previous steps to finish, it cannot effectively use the parallel compute power available in modern hardware. There is also a decay in efficiency as sequences grow longer. As the distance between two related words increases, the path length the signal travels through the network grows. This makes it difficult for the model to maintain the memory capacity needed for long-range dependencies. Recurrent models created a computational ceiling for natural language processing. Scaling machine intelligence to larger datasets required an architecture that could function without these sequential dependencies. In 2017, researchers at Google proposed a different thesis in the paper "Attention is All You Need." They suggested dispensing with recurrence entirely and replacing it with a pure self-attention mechanism. This design moved the network from an ON linear chain to a model with an O1 maximum path length. With a constant O1 path length, the network relates signals from any two positions in the sequence in a constant number of operations. It does not matter as two words are adjacent or separated by hundreds of tokens. The computational distance remains the same. This removes the temporal bottleneck. Instead of feeding data forward point by point, the model can process the entire input sequence at once, shifting the workload into highly parallelized batch matrix multiplications. The transformer architecture traded sequential recurrent memory for spatial calculation. This structural change allowed models to finally utilize the full capacity of modern parallel processing. The process begins by mapping an input sequence of symbols into continuous representational embedding vectors. This gives the machine a numerical format it can manipulate. From there, the model applies learned linear projections to map every token into three distinct mathematical spaces: the query, the key, and the value. These matrices function like an information retrieval system. A query matrix for a word seeks mathematical compatibility with the key matrix of every other word in the sequence. The result of this compatibility check determines the weight applied to the underlying value matrix of those specific words. These three matrices, Q, K, and V, are the variables for the self-attention algorithm. They form the mathematical foundation that allows the model to function without recurrent structures. The core computation involves taking the dot product of the query with all keys. Using matrix multiplication, the model determines the relevance of every token across the entire sequence simultaneously. However, high-dimensional dot products present a technical hazard. As the key dimension, dk, grows, the magnitude of the dot products can increase significantly. These large magnitudes push the subsequent softmax function into regions where gradients are extremely small. If the gradients vanish, the model cannot effectively update its weights during training. To prevent this, the model scales the dot product by the inverse square root of the key dimension. Once scaled, the softmax function is applied. This produces a weight distribution between 0 and 1, indicating which words are most relevant to the current token. These weights are then applied to the value matrix, V, producing a context-aware output. The scaled dot product is the mechanism that allows the network to calculate contextual importance in parallel without suffering from mathematical instability. Relying on a single attention function has a drawback. Averaging a single full-dimensional vector can inhibit the model's ability to attend to multiple semantic meanings at once. The solution is multi-head attention. The model projects the Q, K, and V vectors H times using different learned projections. In the standard transformer, H equals 8 parallel attention heads. To keep computation efficient, the dimensions for each head are reduced to 64. These 8 attention functions run entirely in parallel, allowing the model to represent the data in 8 different subspaces simultaneously. The 8 outputs are then concatenated and projected one last time through a weight matrix to return to the model's original dimensionality. Because the dimensionality of each head is reduced, the total computational cost of multi-head attention is nearly identical to single-head attention. This allows one word to relate to different aspects of the sentence, such as grammar, tone, and subject, across different heads at the same time. A model with no recurrence or convolution processes all input matrices simultaneously. This presents a specific technical challenge. Without a step-by-step process, the model has no inherent way to distinguish the order of words in a sentence. To solve this, the researchers added positional encodings directly to the input embeddings at the bottom of the encoder and decoder stacks. These encodings use sine and cosine functions of different frequencies. Each dimension of the positional encoding corresponds to a sinusoid, creating a geometric progression. Choosing sinusoids over learned embeddings allows the model to learn relative positions more easily. Because any fixed offset can be represented as a linear function, the model can generalize to sequence lengths it didn't see during training. Positional encoding is the geometric method used to provide sequence information to an architecture that otherwise only understands static spatial matrices. This complete diagram shows the transformer's macro architecture. It consists of an encoder stack and a decoder stack, each containing 6 identical layers. Surrounding the attention and feed-forward sublayers are add and norm blocks. These residual connections and layer normalization steps stabilize the gradient flow. They prevent the mathematical signal from degrading as data passes through the deep layers of the network. The effectiveness is visible in these attention head weights. We see what the model actually learned. The heads independently developed anaphoron resolution, mathematically linking the pronoun its back to subject's law and application, using purely spatial attention logic. The empirical results confirmed the breakthrough. The big transformer model achieved a 28.4 Blue score on WMT 2014 English to German translation, reaching a new state-of-the-art after just 3.5 days of training on 8 GPUs. By replacing sequential iteration with parallelized O(1) matrix multiplication, the transformer provided the scalable architecture that allows modern large-scale language models to function.